Hello, my name is I'm a professor here at the University of Cyprus. Our team, the Biotechnology Laboratory, is part of the Mechanical Engineering Department, and we participate in ICARUS projects aiming to develop thermoelectric materials and devices based on recyclable silicon from PV industry. In this video, we will try to show you some of the procedures to follow to give you an idea about the development of the process.
Hello, I'm Silicide, a PhD student in the Department of Mechanical and Manufacturing Engineering at the University of Cyprus. To understand our work, I will explain a bit about thermoelectric devices. Such devices produce power when there is a temperature difference between their two sides. Here is a sketch that shows a thermoelectric device. It consists of a P and N-type thermoelectric legs that are connected electrically in series and thermally in parallel. Thus, when there is a temperature difference between the two sides, then a current will pass through the closed circuit. Such devices are used in thermoelectric applications to recover waste heat in power plant or automotive or other applications.
The experimental process is divided into the fabrication and characterization of thermoelectric materials and the development and characterization of thermoelectric modules.
Let's start with the fabrication of thermoelectric materials.
Its synthesis is carried out by using the mechanical alloying method. Appropriate stoichiometric amounts of reagent elements are mixed in a glove box, and ball milling takes place for several hours depending on the composition under argon atmosphere. At the end of the synthesis process, powder X-ray diffraction analysis is performed to test the product purity and quality. After the validation of the desired silicide phase, high-density pellets of various diameters are fabricated by hot press sintering. Then, thermoelectric characterization is realized. First, the thermal conductivity is measured on the resulting pellet in the temperature range 300 to 780 Kelvin using a NETS LFA laser instrument. Moreover, the electrical conductivity and Seebeck coefficient is measured by using a ZEM3 UVAC RICO at temperature range up to 800 Celsius. Finally, the thermoelectric power factor and figure of merit ZT are determined through the data analysis of the three measured thermoelectric properties.
For the development of thermoelectric modules, design and modeling are conducted using appropriate software tools. For the thermoelectric module manufacturing, selected thermoelectric pellets are parallelized, ground, polished, and diced into small thermoelectric cubes. Cubes are then cleaned and using physical vapor deposition are coated with various thin film metals. Metal coatings act as thermal and electrical bridges, diffusion barriers and adhesion buffers between the thermoelectric semiconductors and the metal interconnects and the bonding material of the thermoelectric module. At this stage, thermoelectric legs are ready to be assembled into thermoelectric modules. Another critical component of the thermoelectric modules are the ceramic circuit boards that are used to connect electrical in series and thermally in parallel with thermoelectric legs clamped between them. Available sizes of such ceramic circuit boards facilitate testing and scalability from proof of concept devices to full-size devices. A key component of a thermoelectric module is the thermal bonding between thermoelectric legs and the metal interconnects of the ceramic circuit board. Poor quality bonding would lead to high electrical and thermal contact resistances, which can be detrimental for the module's performance. As such, the contact resistance of the metallization and bonding are tested through the transfer length method and the scanning probe measurement respectively. Finally, all the components can be assembled and thermally bonded for the fabrication of a thermoelectric module. Wires are connected using soldering to the finalized thermally bonded module. Thermoelectric modules are characterized for their power generation capabilities at various temperature gradients using an in-house testing equipment.
If you want to learn more about the project, feel free to check our website and as well as our LinkedIn account.